back to a few weeks ago when we derived the momentum equation, we had this right-hand side external forces on the control volume. So I'm going to draw the control volume again. That's the control volume, CV. And we said the rate of change of momentum is equal to some external forces, Newton's second law. And in the external forces, we only included the surface pressure, which is obviously always the case when you have internal flow. So these are forces coming from the surface pressure and the gravity force, right? Gravity force. Summed all over the control volume, because this is written for the element, so you have to integrate it over the control volume. But look, in the real life, this control volume, you also have shear stress. Examples, for example, we have a flow. This is surface, and this, you got a flow here, right? You all know that the velocity profile is like this. At the wall, your velocity is 0, v is 0, u is 0, and then here u max. Then you go to constant velocity. So even though we say the inlet are constant, near the wall your velocity is 0. So you get a profile that is non-uniform. So what's the reason for that?
Friction.
The friction, the shear stress. So if I want to have the correct form of momentum equation, the very, very correct form, I have to also include the friction or shear stress. We had it in the beginning of class, the shear stress is equal to mu du dy. It's proportional with the gradient of velocity. If I can somehow include this, and obviously it's a surface integral because it only acts on the surface of this control volume, then I'm just ready to do momentum with viscosity, with shear, and they call it viscous momentum equation. This is inviscid. So this was called inviscid, and viscid momentum Euler equation. Euler EQ. Now today we want to find viscous form of this. Should I start from scratch? No. This is the same. That's the rate of change of momentum over the entire control volume integrated. This is the external force. All I need to do is add the viscous effect to the term that I already have. Alright, so let's do that. In order to do that, I'll just go back to the equation I had for shear stress. And I want to generalize that to the 3D because this object, the control volume, this is in 3D. It's a potato in 3D. Right? So I have to generalize that in 3D. So what I'm going to do, I'm going to take a small Cartesian element in 3D space. So let's do the XYZ coordinate. X, Y, Z. And this is your element. Here we go. So here you have at every face of this element, you have 3 shear stress. One is called normal shear stress. Let's show that is tau sub xx. Right? That means tau in the x-axis and the x-plane in the x direction. And there is another one. I need to use right. So this is tau xx. This way. So shear stress in the x-plane, that's the x-plane, in the x direction. There is another one. Use red. And there is another one this way. So the second one is the shear stress in the x-plane, but in the y direction. And the last one is the shear stress in the x. So the first subscript is the plane. This plane is here. It's in the x. The normal of this plane is the x, but in the z direction. So at every single of this plane for the element, you have 3 of them. So the total is how many shear stress you have? If you have 3, X plane, Y plane, Z plane, and each one of those you have 3 in the plane. So how many is the total? 9. So in fact, the way they show that, this is, we're not going to do that, but they show it in the matrix form. Tau XX, tau XY, tau XC, tau YX, tau YY, tau ZZ. So they combine all into a matrix form. Tau Z, X, ZY, and ZZ. You see the one on the diagonal are just the normal shear stress. But look, we can also say that we have this. In fact, this equation will relax to this equation in the term of gradient when you have one-dimensional flow. That means the only gradient is in the y direction. Now we can generalize that to the 3D space by writing tau is equal to mu times gradients of velocity. That's a generalization of this. So instead of saying du dy, this is the gradient. You say grad of velocity times mu in general, 3. This equation will be derived from the shear stress tensor later in the graduate school. You do some assumption, and then you derive this from out of the shear stress tensor. Now, when I do the derivation, I use that, but when I substitute value, I don't substitute the matrix, I substitute this relation to simplify the equation for you. So let's do that. So what term should I add to this in order to make it viscous? I'm not going to write it again. All I need to do, add one more thing. That term is the surface integral tau dA. What is that? Consider a surface element with dA. Because I need for surface I use S. Let's be consistent and use S. Yes. So what does it mean then? That means that if you take an element on the surface and the flow is moving this way, there is a reaction, tau, the shear stress. And the force is what? Tau dF is equal to tau dA. So you're integrating all those surface forces to add together to put in a momentum. Why? Because you're trying to find the external force. Now this is a momentum with shear form added. You see that the shear stress is added. Last time we did implicit momentum, we assumed that this is 0. Now added. So what's the next step? This is momentum with viscous. It's called viscous momentum, or aka Navier-Stokes equations. In fact, they call all those 5, including continuity and energy, all of them, they call them Navier-Stokes equations. But it's mostly because the first people who did the shear added to the Euler equation, the Navier-Stokes. 2 people did that contribution to the shear. Now, today, in the chapter 7 of your book, it's talking about differential form. So differential form, we want to convert this. This equation goes right here. This equation is written for a general, large control volume, CV. We are interested to find the form of this equation, or of this equation, written for the small element only, written for a small element. This type of equation called differential form. This type of equation is called the differential for right? So in order to get the differential form, obviously we can use the divergence theorem. Let me write the divergence theorem one more time here. Integral of f dot ds is volume, this is surface integral, closed surface integral, is a closed volume integral, divergence f dv. Or they write this, f dot n ds. Dot n, but this vector ds is a scalar, the area of that tiny surface area. So that we had this before, the divergence theorem, and now we are going to apply this theorem to the term that was surface to make everything in the term of volume integral, and then factor out all the volume integral one side and get the inside the integral, and then we end up with differential form. So let's do that here. What I'm going to do, I'm going to rewrite this equation using the divergence theorem. That's the divergence right here. Divergence theorem. So I start with this term. This term is already in volume form, so I just leave it like that. I shall T volume integral rho v dv plus the second term is the surface integral, right? If I want to convert this to volume integral, what should I do? See? All I need to do, this is your f. That's your f. Look at here. Your f here is this term. You see f dot n ds. You see that? So you're going to write here divergence of the volume integral, divergence of the f. What's the f? Rho v. V. Double v. Divergence of that dv is equal to, this guy is the surface integral. You convert it to volume integral. So you get negative surface integral become volume integral, divergence P and the normal pressure part dv plus, look at this term. Again, this is also volume integral. Just leave it like that. So you have volume integral rho vector g dv plus the last term, the shear stress, you use divergence theorem. You have volume integral divergence half dv. You see? Right now, in fact, this ds is like this. N tau dot n es, but this also vector. Right, just like we did it here. Then you have divergence of tau n, the normal n, that is already dot with n. Divergence of f dv. Everything now is volume integral. What does it mean? Everything is volume integral. What should I do? Bring everything in one side. So that's what I'm going to do. So I say the volume integral, right? Take this derivative inside, rho v plus divergence rho v p plus divergence pn minus rho g minus divergence pn, the normal dot product. Take everything to the left side, plus dv is equal to 0. You agree? So what I did, I factor out all the volume integral, so you just take this, the ddt to the inside the integral, so you get ddt rho v plus divergence of rho double v plus, now you bring this to the left, it's negative, you go positive, divergence p dot n minus rho g minus divergence of tau n, which is time dv is equal to 0. Now, an integral over a finite space is 0. What does it mean? This guy must be 0. For arbitrary space, this must be 0. So this is the differential force in chapter 7. So I write it this way. Partial t rho v plus divergence rho v v plus divergence Pn minus rho g minus divergence tau n is equal to 0. As you can see, there is no integral. Do you see any integral in this equation?
No.
It's called differential form, chapter 7. And it's very useful if you want to find, for example, velocity profile. So you have a pipe and you want to see the velocity profile inside it. We have never done it so far, right? So, okay, let's rearrange this. So what I'm going to do again, I'm going to keep these two terms on the left side, and I'm going to take these guys to the right side and simplify it a little bit. So I end up with the more traditional way. So if I do that, I get what? I get partial t rho v plus divergence rho v v. Take this to the right, negative divergence Pn, call this Pn, plus rho g, and then plus divergence tau n. Is it? That's a momentum equation. It's called general compressible viscous momentum equation. Right here, general compressible. Why? Because I haven't taken this row out. I will reach that soon. Compressible momentum, viscous momentum equation. Momentum equation. On top of that, we just go ahead and simplify things, right? So let's write it here. I do the same for continuity or conservation of mass. We had it in this form. Rho dV plus surface integral rho v and the PS is equal to 0. That was the conservation of mass integral form. You see, I want to find differential form. What do? Convert this using divergence theorem to volume integral. So you can write this as this form. Pt volume integral rho dV v plus this becomes volume integral divergence rho v dv 0. Factor everything, what you get? This is differential form. Continuity. You see, do you see any integral here?
No.
With the differential. These are all derivatives. So you have that, and you have this, right? Now, let's get this equation and work on it. So this equation, you have this partial t rho b plus partial plus divergence of rho double b is equal to, you see, when you take the divergence of this thing, only is derivative to the normal direction of that direction. Like if you do it for x equation, you get dp dx. If you do it for y, you get dp dy. If you do it for z, you get dp dz. The other one becomes zero because you get the normal one. So here, that will convert to gradient. So you get negative gradient of p, pressure. And then the next thing is plus rho vector g, because this is a three equation, it's not one equation. So you can also g, the scalar, 9.81. You have gx, gy, gz in three directions. And then the last thing, plus divergence of tau, right? You remember I said, it was right here, I said tau was what? Mu gradient velocity. You remember I said that? So substitute here instead of tau is what? Mu velocity gradient. So what do you get? The final form? Not the very final form, but close partial t rho v plus divergence rho v is equal to negative gradient p plus rho g. And this guy you get plus divergence of mu gradient velocity is equal to the left hand side. Right? So that's this equation that is time dependent. It's not the steady state. You see you have dET. It also can be compressible or incompressible. And also it is viscous. And the viscosity of mu can vary in the space. Right? You see? You have the gradient of that. If we assume mu is constant, you can take it out of that. That's what I'm going to do for constant viscosity. Constant viscosity, you can write it like this. dET rho v plus divergence rho v is equal to negative gradient pressure plus rho g plus mu divergence of gradient of velocity. Can you tell me what does that mean? Divergence of gradient velocity. If you did your calculus very well, and you remember that we have divergence of gradient of A, any quantity is what? Divergence gradient of any quantity is what? L2 of that thing. They call it Laplacian. It's in fact second derivative. How do you define this? L2? L2 is this. L2A is the second derivative of A with respect to A with respect to X plus second derivative of A with respect to Y plus second derivative of A with respect to Z. Laplacian. Call it Laplacian. Now, instead of that, instead of divergence gradient, I can say L2 B. Alright? So I'm going to write it here. And this time I'm going to expand this term. And I'm going to substitute continuity equation. So we get to a nice relation. So expand that. You get, if you expand this, you get d rho dt times v. d rho dt times v plus rho dv dt. That's the expansion of the first term. Expansion of the second term is this. Divergence of the first two So I take these two as one, and the other one as the other one. So I expand the divergence of rho v times v plus rho v times gradient v. That's what I did to get Bernoulli equation. You remember that lecture? Rho v times gradient v is equal to negative gradient v plus rho g plus, for that I assume you get constant viscosity, that means take the mu out, and then you get mu times del Q v. Right, look at this equation. Factor v, you see this term with this term, these two terms, combine them together, what do you get? You get v times rho t plus divergence rho v. Do you agree? We can factor out the v. Do you agree? Yes. For this. So what's this? What's the value of this term? Partial rho partial t plus divergence rho v. What is that?
Would it be 0?
Yeah, it's just, look, where's the continuity equation?
Because there's
Yeah.
no time.
No, there is time, it's time dependent, but look, because that term is 0, even if we have time dependency, this term is 0. So 0 times v, 0. So the only non-zero is this term plus this term and the rest of it. These are non-zero. So I'm going to write that here. So you're going to get rho times dv dt plus rho v gradient v, negative gradient pressure, plus rho g plus mu del 2 v. That's the final form we use in this class. So is this incompressible or compressible? It's compressible. We didn't make an assumption so far. Is it incompressible, uncompressible? The reason that this becomes 0 is because it's continuity. And this continuity is very full, even compressible, right? Now, if I take this rho out of this integral here, and I say derivative of rho with respect to t plus rho times divergence of v. That is what? Incompressible. The assumption of rho is constant. But this is not incompressible, it's general. So I am going to write these equations here, and then we solve some problems. But before that, I don't want to write them continuity and this equation, momentum. Right? I'm going to write it. And then I'm going to expand them for all dimensions, x, y, z. So this first equation, d rho dt plus divergence rho v is equal to 0, conservation of mass. And the second one, d rho v, d dt rho v plus v. I'm sorry, I already simplified it to, where did I put the final form? Right here, right here. I already did substitution of continuity and all those things, so I use the one on the right, on the top. So rho dv dt plus rho v gradient of B is equal to negative gradient pressure plus rho G plus mu del Q B. So this is compressible conservation of mass, and this is compressible conservation of momentum, and it's viscous, transient, viscous, time-dependent, but constant. Constant what? Constant? Viscosity, mu. Mu should be same in the field. If it's not the same, you have to solve the original one that I simplified to that. Can you tell me how many equations are these?
6. The 3 for each one. 4.
You said 4?
1 for continuity and 3 for.
Exactly. Oh, I forgot your name, by the way.
Michael.
Michael, last name?
One of them.
Oh, no, no. Yeah. These are 4 equations. These are not 2 equations. 3 for that. Why? Because velocity are Vx, Vy, Vz. Right? And rho is just density scalar. So 1 equation here, 3 equation here, 4. 4 equation is 2-dimensional space. In 3-dimensional space. How many equations in 2-dimensional space?
3.
Just 3. You see that? And don't forget, there is also an energy equation. You remember last class we did? But today we are not going to consider that today. Alright? We're going to come back to that later. So, 3 plus 1, 4 plus momentum, 5. We have 5 equations for fluids in general. And if you can solve that 5 equation, you can explain every single phenomenon in the fluid. Alright? Alright, so let's work on this and make it more, make it more practical. Consider V, right, is equal to U, I, plus V, J, plus W, K. So the velocity vector, I'll take U, this symbol for X, V, this symbol for Y, and W, this symbol for Z, component of velocity. So if I substitute here, I get this equation. Can you write it? So partial T plus divergence. So if you expand this divergence, so instead of V, substitute, if you do rho V, you get what? Rho U I plus rho V J, right? Plus rho W K. Can you agree? You just do rho times the velocity vector. Now divergence of that is what? You get d dx rho u, right? Plus d dy rho v plus d dz rho w, 0. This guy is the continuity equation. Now you see that there is no gradient, no mathematical, it's just a derivative. You see, that's the reason I call it differential form. In your book, call it differential form. Now, let's go to this equation. What do I get for the u component? Let's take the u component. If you substitute u here, what do you get? You get rho du dt plus u du dx plus v du dy plus w du dz is equal to negative gradient p is gradient d. You see, this is dp dx I dp dy k plus dp dz k. But you are only concerned about I component. This is just a u I component, right? So you get negative p dx plus rho g. rho the x component of G. In general, we know that, well, usually we take G down, but let's say G has x, I, y, j, z, k. This is general form, right? So you get rho in the x component of G plus mu. What do you get for that? The second derivative of u x squared plus second derivative of u y squared plus second derivative of u omega squared. This is the momentum in the x direction. Momentum in the y direction. Rho partial t v instead of u, you have v plus u dv dx plus v dv dy plus w dv dz is equal to negative p y, and there is the second y plus rho component of g y plus mu, the second derivative of v with respect to x plus second derivative of v with respect to y plus second derivative of v with respect to z. So this is momentum in x. So this is conservation of mass. X momentum. This is y momentum. And this is z momentum. Let me write z momentum here. Rho d dt w plus u derivative of w with respect to x, v derivative of w with respect to y plus w derivative of w with respect to z, negative gradient pz plus rho gz plus mu, the second derivative of w with respect to x squared, the second derivative of w with respect to y squared, plus second derivative of w with respect to z squared. What type of equations are these? Differential equations. More accurately, they are called partial differential equations. Partial, why? Because you have the partial derivative, partial with respect to x, partial with y, partial with z. You see that? Now, if you can solve this, you know you don't need to pass the course of fluid mechanics or fluid mechanics 2 or compressible flow or gas dynamics or turbulence. All these courses you already know it if you can solve it instantly. But the problem is this term, you see, is nonlinear. You multiply u by itself, the gradient itself. This term they call it convective term. They are due to the motion of fluid. And this term makes this equation to be unsolvable. It's still in the current century, after these many years, this is one of those a few 8, 6, 7 problems that human being cannot solve analytically with pen and pencil. So what they do, they approximate this on computers. They linearize this on a computer and then they solve it. So that's not the subject of this class, that's another course. It's called computational fluid dynamics. But in order to understand everything in this class, right now, hopefully, I'll be able to solve one problem. What you do, you write these equations, and then step by step, because most of the time the problem is what? The steady state. If the steady state, what happens? You get rid of all these time-dependent terms. And then most of the time, some of these terms are zero. So you end up with a simple equation that you can handle. Right? So that doesn't mean that every single time you see the problem like this, you say, well, I've got to have a computer, I can't solve it. No, in most cases, not most cases, in many cases, you can solve this analytically, and there are already a lot of solutions in the literature. Right? In fact, there is a book that has collection of all the solutions done by various people. They start from 1875 or 1880 all the way to today. They have different names. So, right, what I'm going to do right now, I'm going to just show you, for example, one of these problems is called Poisson flow. One of the guys who actually solved a special case of that. So I'm going to show you how many terms you drop in the simple case that I'm going to talk right now. Let's say you have a pipe, right? That the flow is coming here. Flow is coming in. And the flow eventually, what happens when the flow enters this, you have some sort of, you see the velocity here is 0 in this end, but it's not 0 here. So you have some sort of called boundary layer. But at some length, they will merge, these two boundary layers, they will merge, and you have a uniform velocity profile like that. You see that? At any point, you have a uniform velocity profile. So if you continue into infinity, you have a velocity profile like that. It's maximum, Vmax, at the center, and it's 0 on the walls. You see that? And the pattern is pretty much the same. You know, if you take this as your x-axis, you can take it as y or z, but I want to take that as my x-axis. Any derivative in the x is 0. Do you see that? Because the pattern is same. The pattern is same. So let's call it v, not v, u max. So you see the pattern, the center is max, and then it eventually goes to 0 on the wall. So if I want to find this profile, now the question is find the profile for u versus y. So let's say this is your x, and this is y. Starting from here, let's say this is your x, and this is your y. You see that? Put your coordinate system there. So x is the x-axis, y vertical, and now the question is find uy. How do you find it? Are you going to guess it? Well, one way is just to the way we did it in chapter, I think chapter 2 or 3. We guessed a parabolic profile like ay squared plus by plus c, and then we applied the boundary conditions here, and we got some parabolic distribution. But that was not any physics behind it. Now the question here is, get that velocity profile starting with negative slopes. So this is a totally physical, real thing. So we are doing real thing, we're not just guessing. All right, so how can I do that? For that problem here, you see, this pattern will continue forever. Do I have changing time? Do I have any changing time?
No.
So these are 0. Any ddt is 0. What about variation in the x? First of all, do I have v component? Do I have vertical component of velocity? Velocity is always in the x. Do I have v? No. Do I have the omega or w? The w is the component velocity here. That means the flow is going this way? No. So this is 0. So from this equation, you see, you get what? This is also rho. This is equal to 0, right? So if this is 0 from this equation, come here. What about this term? Do I have omega? No. Do I have v? No. This term is also 0 from the continuity equation. You see that? So what about this term? I don't even have v. Everything here is 0. Everything here is 0. All of them 0. So the only non-zero was this guy, which because it's 0 is 0, and then this guy is non-zero, right? Do I have the vertical thing? The vertical thing is in the y. Now let's say we don't even have mass. The flow is, the pipe is so small that the weight of the flow is not important at all, right? So g, I know g is in the y direction, But the value of gy can neglect it because it's very small, right? And there is nothing in the x. So you get that term, and out of this term, this is 0, why? Because the first derivative is 0, the second derivative is 0. This is non-zero, but this is also 0, there is no w. But you see u with respect to y will change, so you have the second derivative. So this equation will simplify to this. Del p x plus mu, the second derivative of u with respect to y. You see that is equal to 0. What about this equation? The second equation. Well, the second equation, talking about v, everything is v. We know that v is always 0. And there is no change. That means 0 is equal to 0. That means dp dy is 0. The pressure in the y direction is 0. That's it. So the second equation, dp dy, 0. And the last equation is just 0 because we don't have. So can you solve that?
Okay.
It's a differential equation. It's simple differential equation. You can solve it. If I say P is this, P is equal to P0 plus X, P max minus P0 divided by L, the length of the pipe from here to here. Then what do you get for dP dx? That's dP dx. Then you double integrate it with y. Then you get the second order. You apply the boundary condition, one here, then you get a velocity profile. It comes out of natural source. So you can't say, well, you know what, I made the assumption it's parabolic. No, it's physically parabolic because you solve natural source. The first person who solved it, his name was Poisson. It's a French, I don't know how they read it right here. He's got a very weird name, but Poisson flow, something like that.